updates on thermochemistry. Today we're going to get away from exothermic and endothermic reactions and look at a heating curve. So we'll show you what a heating curve is, and then we'll look at how much energy it takes for water to go through different phase changes, going from solid to liquid to gas. So a heating curve is a graph of temperature versus time. Temperature is going to go along the y-axis, and time will be on the x-axis. This is going to describe the enthalpy change that takes place during phase changes. So as you can imagine, the more temperature you've got, the more enthalpy you'll have. So when a solid substance is heated, its temperature will increase until it reaches its melting point. We're going to abbreviate melting point as MP. The temperature will then stay constant during the melting process. This is something that students tend to have a little problem understanding. We're going to do a lab to see this actually happening, but it's something that most students have a little bit of trouble with grasping. But I think when you see the heating curve and you see the demonstration, it should help keep that into your minds. So when a substance is completely melted, its temperature again starts to increase as we add heat until it reaches its boiling point, which we're going to abbreviate as BP. The temperature will stay constant again during boiling. Until all the water has boiled, the water will stay at the same temperature. Once all the water has vaporized or boiled, the temperature starts to increase again, and in this case we're in our gas phase. So heating curve problems involve two types of calculations. One is the temperature change. This should look familiar. This was calculating the amount of heat using the mass of the substance times its specific heat and the change in temperature. The dimensional analysis using delta H, which is where we're going to be using that enthalpy calculation, where there's a flat change or a flat line, the mass is going to be the known, and you'll see in our example. This becomes a very easy part of the problem. So we'll be using something called the molar heat of fusion, or the change of the heat of fusion. This is the amount of energy required to melt a substance, or going from solid to a liquid. You'll always be given this molar heat of fusion. You'll also have molar heat of vaporization. So this is symbolized by delta H for vaporization, and you'll always see these little indications down here. It'll either be solid or usually it's fusion, because that's the process of going from solid to liquid, and vaporization is the process of boiling or going from liquid to a gas. So let's take a look at a phase change diagram that has all of our variables in place. So here's a question that you would be asked. What's the total amount of heat in joules that must be added to 165 grams of ice, which is solid water, that is currently at a temperature of -5 degrees Celsius, and then bring it all the way up to steam, which is at a temperature of 103 degrees Celsius. So here's our starting point. We're starting at -5 degrees Celsius. We're going to bring it up to the point at which it would melt, which is 0 degrees Celsius. Now the formula you're going to use for this section of the line going from -5 degrees Celsius to 0 is going to be the amount of heat or energy, Q, equals the weight of the water times the specific heat of ice, and then the change of temperature. We're going 5 degrees. We're actually bringing it from -5 to 0, so that's a change, or delta T, of 5 degrees. The next part of our graph is a flat line, because remember, our temperature is not going to change as we go through this change. It's going to stay right at 0. We're going to be using a different calculation for the melting, which is the delta H of fusion. The next line segment means that all of our water, or sorry, all of our ice has melted, and now this is the liquid phase. And the liquid is going to increase as we go along time. It's going to increase in temperature, until you reach 100 degrees Celsius. You're going to use the same formula. The amount of energy it takes to change the mass of your water times the specific heat of water, the number of degrees, or a change in delta T. Well, we're going from 0 to 100, so our delta T is going to be 100 degrees Celsius. The next part is when we're taking our liquid and we are basically vaporizing it. We're turning it into gas. And again, the temperature is going to stay the same here. So we're going to use the delta H of vaporization because we're going to boil all this, and the temperature will be staying the same right at 100 degrees until all of the liquid has turned to vapor. The last part of the line is our gas phase. Again, same formula we've been using before. We're going to figure out the amount of heat it takes to get the mass of the water we have, 165 grams, times the specific heat of water, which you'll be given. And then the delta T in this case is we're going from 100 degrees to 103, so it's only going to be a delta T, or a change in temperature, of 3 degrees for this portion of the graph. You'll always be given these constants. Except for this one, the specific heat of water, you already know that. It's 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. But this is all in joules, so I want to be sure that I'm using the joules for the water. So a lot of information here. You're going to see that this is actually going to require 1, 2, 3, 4, 5 different steps to calculate this. So I've made my graph a little bit smaller here. It is really helpful to use this graph even if you have to sketch one, but normally you're going to be given this. So here's the question again. What's the total amount of heat in joules that must be added to 165 grams of ice, which is solid H2O, that is currently at -5 degrees Celsius to change it to steam at a final temperature of 103 degrees Celsius? There's the information I'm given. So here's my first calculation and the formula. So this is the ice portion of my graph. Q equals, there's the weight of the ice, the specific heat of ice, so right there, specific heat of ice, times the change in temperature, which was 5 degrees. We went from -5 to 0, so it's a change of 5 degrees. Your answer would be 1,660 joules. Now we're ready for the next portion. So for this, we're going to be looking at the amount of energy you need to melt the weight of ice. So here's our weight of ice times that delta heat of fusion. Well, it takes 6.10 kilojoules per mole to get is our delta H. Now we've got water. Because we've got grams of water, we need to find out how many moles, because remember this was per mole. So first I have to figure out how many moles. So there's my conversion factor, 18.02 grams of water in 1 mole of water. Make sure my units cancel out. Now 1 mole of water, my conversion factor is 6.01 kilojoules per mole. So that's expressed right there. Now I have to keep going because again I've got kilojoules here and my units are in joules. So 1 kilojoule is 1,000 joules. Now I have joules as left over as my unit, and there's the answer. Now I go on to the third part of the graph, right here, where I'm taking the liquid water to the final temperature here of 100 degrees. There's my weight of water. Now I have to grab the specific heat of water, which you already know is 4.18 joules per gram per degree Celsius. And the delta T here is we're going from 0 to 100. So that's going to be 100 degrees Celsius, which will give me a figure, the amount of heat that it's needed to change this water's temperature from 0 to 100 is 6.90 times 10 to the 4 joules. Now I'm on to segment 4. I'm going to be using this same sort of calculation for the graph section 4. So here's the weight of the water. I need to find out how many moles I have. So there's my mole conversion. 1 mole of water has a delta H of vaporization of 40.7 kilojoules per mole. So there's my calculation there. Have to convert back into joules. And there's my answer. One last little bit to do. Same formula I've been using all along. You can see that when you've got a tilted part of the graph, you're going to be using this formula. When you have a flat area of the graph, you're going to be using this formula. And this is just using dimensional analysis calculations. So here we are, 165 grams times the specific heat of steam. I'm getting that right off my chart here. And I'm only moving at 3 degrees Celsius. I'm going from 100 to 3 degrees, 103 degrees Celsius, so delta T of 3. Calculate this out. Now I've got all 5 parts. 1, 2, 3, 4, 5. Add them together, and that's the amount of energy it's going to take to move 165 grams of ice that's at -5 degrees Celsius, changing it into steam that's at a temperature of 103 degrees Celsius. A lot of little steps in this calculation, but you're doing the same thing over and over again. You're just looking at your line, inserting the correct calculation, and moving on to the next one. All right, let's see if you are ready to practice. There's nothing for you to write down here. You don't have to worry about taking one of your practice ones. We'll be practicing this together at the practice station.